Alright, welcome back again to this video lecture in ENSC112. Now, this is our second problem for our first topic. Okay, the problem is taken from the textbook by Central, and this is problem 1-126, page 62. The problem says that the heat generated in the circuitry on the surface of a silicon chip, which has a thermal conductivity of 130 watts per meter Kelvin, is conducted to the ceramic substrate to which it is attached. The chip is 6 millimeter by 6 millimeter in size and 0.5 millimeter thick and dissipates 5 watts of power. Disregarding any heat transfer through the 0.5 mm high side surface, determine the temperature difference between the front and the back sides of the chip in steady operation. Okay, so here is our chip. Here's the silicon chip, and it is on top of this ceramic substrate. The dimension of the chip is 6 millimeter by 6 millimeter and a thickness of 0.5 millimeters. And it says here that the chip actually generates power or dissipates power, 5 watts. Okay, so how do we know if this is conduction or convection or radiation? Now, first is there is no airflow, and we can also check the given value is K, so that's a problem of conduction rather than convection. And we have the sizes, so we can actually get this is a heat transfer across a medium. So now how do we solve this? Let's just illustrate first the problem. So what it means is we have to provide illustrations wherein we can be able to express the heat conduction phenomenon. Right, so here's our chip, and the heat flow is, because it says here, is conducted to a ceramic substrate, so that means that the heat is like this, going to the substrate, and this is 5 watts. And here's our thickness, right? This is the 0.5 mm, and this is delta x. Okay, the area, we have the area because that's the 6 times 6. So area is 6 times 6 is 36 millimeters squared, or in terms of meters squared, this is 3.6 times 10 to the negative 5 meters squared. Okay, so this is actually a straightforward problem again, except that we are asked to find the temperature difference. And so let's write here, applying now the heat transfer, the heat conduction equation. So Q flux is equal to negative Ka delta T all over delta X. Now we are asked to find the delta T. So if we rearrange the equation, what we get is an expression that looks like this. Delta X is, not delta X, but rather delta T is equal to the heat flux. This should be heat rate, not the flux. Right? So it should be heat rate because we have the area. So heat rate times the delta X all over negative what is this? Ka. Okay, so let's substitute all the values. We have 5 watts times the delta X, which is 0.005 millimeter. This should be in meter. So we convert everything to meter, to our base units, watts and meters. So this 0.005 divided by the thermal conductivity, 130 watts per meter, this one meter Kelvin. So take note, by the way, that in terms when we talk about delta T, so we can just say that the Kelvin units, Kelvin is equal to the Celsius. Right, so whenever we are going to solve or multiply to delta T, the Kelvin is just equal to the Celsius, so you don't need to convert one to the other. And this one is, the area is 3.6 times 10 to the negative 5, and again this is in meters. So okay, so for the units we have the watts, we have this one should be in squared, so this is meter squared, so mm, and what's left is the unit of Kelvin. So delta T is equal to 5.34 Kelvin, or we can just write delta T is equal to 5.34 degrees C. Okay, so that's just it. Then we'll do another problem. Okay, the next problem is taken from the textbook by J.P. Holman. This is example 1.2. This is page 18. It says here, air at 20 degrees C blows over a hot plate 50 by 75 centimeter maintained at 250 degrees C. The convection heat transfer coefficient is 25 watts per meter squared Celsius. Calculate the heat transfer. Now you see here, what's given is in Celsius, but as I have said that sometimes, I mean, as long as we're just dealing with delta T, the Celsius and the Kelvin, they're just actually interchanging. Okay, so calculate the heat transfer. Now there's no figure, but we can just illustrate the problem. Okay, so right here we have a heated plate, and the heated plate is, we have a dimension of, this is 75 cm and this one is 50 cm. And we have air that's blown over a hot plate. So let's say here's the air, and so this is right, this is air, and the hot plate is, right, so the hot plate, the temperature of the hot plate, this is TS, so TS is 250 degrees C, and air that's being blown is, so the air T of the fluid is 20 degrees C. Okay, so you can see now that we have the area, we have this fluid motion, we have the temperature difference, then therefore we can just simply solve for the heat transfer. Also, by the way, since Ts is greater than the T of the fluid, then the heat transfer direction would be this way. Right, so therefore, let's just write, this is figure 1, this is a pictorial view, and figure 2, this is something like a detailed view. So let's write here, applying now the convection heat transfer equation. So our equation is Q dot is equal to HA times the difference between the surface temperature minus the fluid temperature. So this is 25 watts per meter squared Celsius, and the area is 0.75 times 0.5, and this is in meter squared. right? This is right here, meter squared, and this is 250 minus 20, and they are in degrees C, degrees Celsius, right? So degrees C, and we have degrees C right here, so that cancels out, and we have meter squared in the denominator, and this is right here, meter squared in the numerator. So if you do the computation, what you'll get is 2156 watts. Okay, so if we can't understand the problem right away, then we can just try to illustrate that, and then at least somehow we can figure out what are we going to solve, or how are we going to solve the problem. Okay, next problem is this. Let's have a more complex problem. Now this problem is taken from the textbook by Sengel, Hidden Mass Transfer, and this is problem 1-66 and page 55. It says here, in a power plant, pipes transporting superheated vapor are very common. Superheated vapor is flowing at a rate of 0.3 kilograms per second. This is the mass flow rate inside a pipe with 5 cm diameter and 10 meters in length. The pipe is located in a power plant at 20 degrees C and has a uniform pipe surface temperature of 100 degrees C. If the temperature drop between the inlet and exit of the pipe is 30 degrees C and the specific heat of the vapor is 2190 joules per kilogram Kelvin, determine the heat transfer coefficient as a result of convection between the pipe surface and the surroundings. Okay, so let me explain first this superheated vapor. Going back to this diagram, so if we have the saturation vapor curve of, let's say, water, and here's our constant pressure line. So right here, this is the boiling point, boiling temperature, freezing temperature, and this one is the boiling temperature. Now if our constant pressure line is, let's say, 100 degrees C, 100 degrees C, I mean 101 kPa, that's the atmosphere, the pressure at sea level. So the water boils at 100 degrees C, and this one is 0 degrees C, starts to freeze at 0 degrees C. So right here, at this portion, the substance, the water substance, is actually in liquid state, right? So it's in liquid state. So it increases temperature. It increases its temperature until it gets to this boiling temperature. From this point onwards, it's gonna change its phase. So it's gonna change its phase from 100 degrees C. At 100 degrees C. So here, this is saturated liquid. We call this saturated liquid, and here is what we call the saturated vapor. So in the steam tables, this is labeled as F and this is G. So again, saturated liquid, it's still in liquid phase, but here this is entirely, 100% in vapor phase. Again, right here, 100% in liquid phase, and here 100% in vapor phase. So in between, there's gonna be a fraction. Now what's gonna happen if you still increase, or you're still gonna add heat to the water beyond this point? Then it's gonna be changed to a region of superheated, right? So this region right here, this is what we call the superheated vapor or superheated steam. Okay, so that's this problem. That's what this problem is talking about. So superheated vapor is flowing at a rate of 0.3 kilograms per second. So here's the pipe, and here's our superheated vapor, and the velocity, not the velocity, but rather the mass flow rate, so this is m dot, is 0.3 kilograms. Okay, so what if we'll just let's write now the given. Okay, so list down necessary information. Okay, so we have m dot is 0.3 kilograms per second, and the diameter we have here the diameter of the pipe. So D is equal to 5 cm. And what else? The pipe is located in a power plant at 20 degrees C and has a uniform pipe surface of 100 degrees C. So we have a surface temperature. So let's just write Ts. That's the surface of the pipe. Ts is equal to 100 degrees C, and the ambient, right? This is ambient temperature, which means that's the temperature of the surrounding air. So that's gonna be 20 degrees C right here. And what else? If the temperature drop between the inlet and the exit pipe of the pipe is 30 degrees C, so delta T between inlet is T outlet. Let's just write T outlet minus T inlet. This is 30 degrees C, and the specific heat, this one specific heat of the vapor is 2190 joules per kilogram. Okay, so the first part is to solve for, since we have this delta T and we have this Cp, then we can actually use we use the thermodynamics to solve for the heat, for the sensible heat. So this is, let's just write solve for heat rejected by the pipe using thermodynamic principles. Okay, so if here's our pipe, right? So we have here the superheated vapor, and let's say here's our inlet, right? So here's our inlet and here's our outlet. So let's say in this inlet we have this T sub 1, and in this outlet we have this T sub 2, right? So this is just an arbitrary point, and the problem says that this delta T is equal to 30 degrees C, right? So in other words, if the outside temperature or the ambient temperature or the air temperature is 20 degrees C and this one is 100 degrees C, then this one is actually, I mean, the reason why this surface is hot is just simply because of the flowing fluid. So in other words, there's going to be heat that's coming, or the heat flow is going to be from this to this, right, to the surface of the pipe, and of course from the surface of the pipe to the ambient temperature. There's going to be heat loss. Okay, so we are not going to consider the conduction here. The conduction allow the pipe walls. For now, let's just neglect that. Okay, so now the question is, what is this Q, right? What is this Q? Because if we know this Q, then we can actually solve for the heat transfer coefficient. So this Q dot is just simply M Cp delta T, right? What is the mass flow rate? This is given 0.3 kilogram per second times the specific heat, which is 2190 joules per kilogram K, times the delta T. The delta T that's given is 30 degrees C. Okay, so this is what I'm talking about, that the Kelvin, whenever there's going to be a change in temperature, take note, this is delta T. So therefore, the degrees C, the change in degrees C is just equal to the change in this Kelvin. Okay, and this is kilograms, this is kilograms. So what's left is joules per second, and this is in watts. Alright, so 19,710 joules per second, or 19,710 watts. Okay, what else is the next step is now from heat transfer, we can now solve for for H. So Q dot is equal to HA times TS minus this one. Okay, we have this Q dot, we have A. By the way, how do we solve for the A? And just take note, this is area perpendicular to the heat flow, but since we are dealing with cylindrical geometry, then the area is equal to pi times d times L. That's the surface area. Okay, so if this is it, and we have a heat flow, let's say from the center radially going outward, then this will be the surface area. That's the area that's parallel to the that's perpendicular to the heat flow. Alright, so what that means is we have this temperature, so H is equal to Q dot is equal to A times the temperature difference. Alright, so what is this Q dot? It's 9,710 watts, right? And the area is just simply pi times d. And what is d? This is 0.05 meters, 0.05 meters times the length, right? Times the length. What is the length? 10 meters times 10 meters, right? Times the temperature, surface temperature, which is, what's the surface temperature? 100 minus 20. So 100 minus 20 in this degree C. So the H is equal to, actually, if you do the computation, what you get is 156.8 watts per meter squared Kelvin. Okay, so that's it. Now let's review what we did here in problem 1.4. So we have this superheated vapor that's going through that's going inside this, or that's flowing through this this pipe, and we are asked to find the convection heat transfer coefficient, the H. So the convection phenomenon would be actually would just be from this point going to the air, to the surrounding air, right? So we have the surface temperature of 100 degrees C, and the air temperature is 20 degrees C. We have everything except that we need to determine this Q. Alright, so of course, if we don't know this and we are asked to find the H from this equation, Q is equal to HA TS minus T of the fluid. If we don't have this and we don't know the H, then of course we won't be able to solve that. We'll be needing two independent equations. So we are going to obtain this Q. We obtain this Q by thermodynamics, using Q is equal to mCp delta T. So this way we have two equations. So here's our first equation, and here's our second equation. So in that way we can be able to solve that. So what we did first was to list down the necessary informations. So we listed that, and then we solved for the heat rejected by the pipe using the thermodynamic principle. Q is equal to mCp delta T. And once we have that, then we can use this convection equation, this basic convection equation, And just take note that the area, of course, that's going to be the area perpendicular to the heat flow. And in our case, since we have a cylindrical geometry, then we need to use this equation, pi d L. That's the surface area of the cylinder. Okay, so we substituted everything and we get this heat transfer coefficient. Okay, so the next problem that we're going to solve is problem regarding heat radiation. So we're gonna do that in the next video.